morning, friends. In chapter 13, kinetic theory, already we discussed some numerical of exercise and illustration. Now the remaining numericals are 13.4, 13.5 and 13.7. 13.6 already we discussed and also 13.9 we discussed. Now next numerical is 13.4 of exercise. Now an oxygen cylinder of volume 30 liter has an initial pressure of 15 atmospheric pressure and a temperature of 27 degrees centigrade. After some O2 gas is withdrawn from the cylinder, the pressure dropped to 11 atm and temperature dropped to 17 degrees centigrade. Estimate the mass of oxygen taken out of the cylinder. So here value of I is 8.31 joule per mole Kelvin and atomic mass of oxygen is 32 atomic mass unit. Now in one cylinder the oxygen is filled. The volume of a cylinder is 30 liter. When the cylinder is completely filled by the oxygen, at that time the pressure is 15 atm and temperature is 27 degrees centigrade. Now, some oxygen is taken out from the gas, from the cylinder. So after oxygen taken out from the cylinder, the pressure is dropped to 11 atm and temperature is dropped to 17 degrees centigrade. So we have to calculate how much mass of the oxygen is withdrawn or taken out from the cylinder. Clear this? Okay. For that purpose, first we write down whatever the data is given. The initial pressure, first the atomic mass, MO2, is equal to 32 atomic mass unit. Right? 32 gram is given here, 32 gram per mole. So gram per mole is equal to 32 into 10 raised to minus 3 kg per mole. Now volume is given 30 liter. That is the 30 into 10 raised to minus 3 meter cube. Initial pressure P1. P1 is given as 15 atm. This is equal to 15 into 1.015. Or the 1.01 into 10 raised to 5 Newton per meter square. Final pressure P2 is 11 atm. Is equal to 11 into 1.01 into 10 raised to 5 Newton per meter square. Initial temperature 27 degrees centigrade. T1 27 degrees centigrade, that means the 300 Kelvin. And final temperature is 17 degrees centigrade after the oxygen is withdrawn. So there is the 290 Kelvin. 290 Kelvin. Now we know that from equation of state, from equation PV is equal to mu RT. PV is equal to mu RT. And also we know that mu is equal to M upon M0. M upon M0. So here we have to substitute the value of mu in terms of the mass because the mass we have to calculate. Therefore, PV is equal to mRT upon M0. mRT upon M0. Therefore, M is equal to PV M0 upon RT. Mass is equal to PV upon M0 upon RT. Therefore, mass of oxygen taken out from cylinder delta M is equal to M1 minus M2. M1 minus M2. Initial mass minus final mass. Therefore, delta M is equal to initial mass P1, V1. Now listen here. Volume is constant, pressure are different, temperature different, volume M0 are constant. Therefore, V M0, or the M0 V upon I is constant into bracket P1 upon T1 minus P2 upon T2. P2 upon T2. V volume of a cylinder is constant, M0 atomic mass of oxygen constant, and I is constant. Therefore, P and T are values initial and final. Therefore, M0 V upon I is taken out of the bracket. So inside the bracket P1 upon T1 minus P2 upon T2. Now we substitute the value. M0 30 into 10 raised to minus 3. 30 into 10 raised to minus 3. Volume is given 30 liter. That means the 30 into again 10 raised to minus 3. M0 is 32. Into 30 into 10 raised to minus 3 upon R 8.314 into bracket P1. P1 is given as 15 into 1.01 into 10 raised to 5 upon T1. T1 is 300 minus P2. P2 is 11 into 1.01 into 10 raised to 5 upon 290. So as we simplify it, we obtain 0.1408 kg. 0.1408 kg. That means the 0.141 kg oxygen is taken out from the cylinder. This is the most important numerical. Again, O2 cylinder of volume 32 liter has the initial pressure 15 atm and temperature 27 degrees centigrade. So initial pressure P1 15 atm, 1 atm is equal to 1.01 into 10 raised to 5. Therefore, pressure P1 is equal to 15 into 1.01 into 10 raised to 5 Newton per meter square. And initial temperature is 27 degrees centigrade. Convert into Kelvin. So 27 plus 273, that is the 300 Kelvin. After some O2 is withdrawn from the cylinder, the pressure drops to 11 atm and temperature becomes the 17 degrees centigrade. Final pressure, that means after the some oxygen is taken out from the cylinder, so pressure, final pressure is 11 atm is equal to 11 into 1.01 into 10 is to 5 Newton per meter square. And final temperature T2 is 17 degrees centigrade. So 17 plus 273, 290 Kelvin. Atomic mass of the oxygen is given 32 gram per mole, and also R is given 8.31 joule per mole Kelvin. Okay. Now from equation of state, PV is equal to mu RT. But here we have to calculate the mass. Therefore, the mu is converted into the mass. So we know that the mu is equal to M upon M0. Substitute in this equation. Therefore, PV is equal to M upon M0 RT. Therefore, this equation of M is equal to PV M0 upon RT. So that is the mass of a oxygen gas in a cylinder at pressure P, volume V, temperature T. So from this equation we can calculate the initial and final mass, and the subtraction of these two masses that gives the mass of the oxygen taken out from the cylinder. Therefore, mass of oxygen taken out from cylinder delta M is equal to M1 minus M2. Initial mass minus final mass. Substitute here. Now we solve mu 0, V and R are constant. Only the P and T are changes. Therefore, M0 V upon R into bracket P1 upon T1 minus P2 upon T2. And we substitute the value of all the quantities are mentioned here. So we obtain the mass of the oxygen taken out from the cylinder delta N is equal to 0.141 kg. Clear? Okay. Now after that the next. And a bubble of volume 1 centimeter rises from the bottom of lake. 40 meter depth, deep at the temperature 12 degrees centigrade. Now the situation is this. One lake, here the depth is given, D is or the edge is given the 40 meter. One air bubble is rises at the bottom. The initial volume is 1 centimeter cube. When the air bubble reaches on the surface, its volume is going to increase. Now here the temperature T1 at bottom is 27 degrees centigrade. 27 degrees centigrade. And at the top is, on the surface, there is a 35 degrees centigrade. 35 degrees centigrade. Here the pressure at the bottom is P1, on the surface there is the P. Now, to what volume does it go when it reaches on the surface is at temperature 35 degrees centigrade? When the air bubble reaches at the surface at 35 degrees centigrade, what is the volume is increased? That means we have to find out the final volume of the air bubble. Initially is V1, on the surface is V2. So initial volume V1 is given. V1 is given as the 1 centimeter cube. That means the 10 is to minus 6 meter cube. Right? Okay. Initial pressure P1 at bottom. That is at bottom. Just read. At bottom, now initial volume V1 is equal to 1 centimeter cube. That means the 10 is to minus 6 meter cube. Right? Pressure at bottom P1 is equal to P0 plus H rho G. Because bottom is at this depth 40 meter. P0 is the atmospheric pressure. Therefore 1.01 into 10 is to 5 plus H 40 rho 10 is to 3 G 9.8. 9.8. So it's equal to 4.93 into 10 is to 5 Pascal. That is the initial pressure P1. Initial temperature T1 is equal to 12 degrees centigrade plus 273. 12 plus 273. So 285 Kelvin. 285 Kelvin. Now, when the bubble reaches on the surface, when the bubble reaches at surface, at that time, what is the temperature and pressure? The pressure is 1 atmospheric pressure. Right? T2 is equal to 35 degrees centigrade. So it's equal to 35 plus 273 is equal to 308 Kelvin. Pressure P2 is equal to atmospheric pressure 1 atm. 1.01 into 10 is to 5 Pascal. What is the volume V2? We have to find out. Again, when the bubble reaches on the surface, so its temperature T2 is 35 degrees centigrade, pressure is 1 atmospheric pressure, and we have to find out what is the volume. Therefore, the equation PV is equal to mu RT. PV is equal to mu RT. Mu and R are constant. Mu and R are constant. Therefore, we can write PV upon T is equal to mu R is equal to constant. Therefore, at bottom P1 V1 upon T1 is equal to on the surface P2 V2 upon T2. Therefore, equation of V2 is equal to P1 V1 T2 upon T1 P2. So from this equation V2 is equal to P1 V1 T2 upon T1 P2. Now substitute all value. Therefore, volume of the bubble on the surface P1 is this 4.93 into 10 is to 5. Volume B1 10 is to minus 6. T2 is our 308 Kelvin upon T1 is 285 into P2 is 1 atmosphere 1.01 into 10 is to 5. So as we simplified, so there is the 5.3 into 10 is to minus 6 meter cube. So the volume of the air bubble on the surface is 5.3 into 10 is to minus 6 meter cube. Initially is 10 is to minus 6. When it is reaches on the surface, the volume becomes 5.3 into 10 is to minus 6 meter cube. So there is also most important numerical. Again, an air bubble of volume 1 centimeter cube arises on the format at the bottom of a lake 40 meter deep at temperature 12 degrees centigrade. To what volume does it grow when it reaches the surface? Is at cap 35 degrees centigrade. So first we note down the quantities at bottom. Volume of the bubble is 1 centimeter cube. That means the 10 is to minus 6 meter cube. What is the pressure at the bottom of a lake? Bottom is 40 meter deep depth. Therefore, P1 is equal to P0 plus H0G. P0 atmospheric pressure 1.01 into 10 is to 5 plus H 40 meter rho 10 is to 3 G 9.8. Now P1 is equal to AG simplified 4.93 into 10 is to 5 Pascal. And also the temperature at the bottom is 12 degrees centigrade. So 12 plus 273, that is the 285 Kelvin. Now when the air bubble reaches on the surface, at that time the temperature is 35 degrees centigrade. So 35 plus 273, that is the 308 Kelvin. Now pressure is atmospheric pressure only act. Therefore 1 atm is equal to 1.01 into 10 is to 5 Pascal. And we have to find out what is the volume on the surface. V2 we have to calculate. Now from equation of state PV is equal to mu RT. Therefore PV upon T is equal to mu R is equal to constant. Therefore we compare PV upon T at bottom and also on the surface. Therefore P1 V1 upon T1 is equal to P2 V2 upon T2. So from this equation, what is the V2? V2 is equal to P1 V1 T2 upon T1 into V2. Again, V2 is equal to P1 V1 this T2 upon T1 and this P2 here. Substitute all value already mentioned here. Therefore V2 we obtain 5.3 into 10 is to minus 6 meter cube. Figure is only for your understanding, not required in numerical. Okay. Now next, estimate the average thermal energy of helium atom at 3 different temperatures. First, at room temperature 27 degrees centigrade. Second, at the temperature of the surface of the sun, approximate 6000 Kelvin, and the temperature of 10 billion Kelvin. What is the average thermal energy of helium atom? So Boltzmann constant Kb is equal to 1.38 into 10 is to minus 23 joule per Kelvin. Now for first, temperature T is given the 27 degrees centigrade. That means the 27 plus 273, that is the 300 Kelvin. A base thermal energy or the kinetic energy, a base thermal or kinetic energy. Why that is known as the thermal energy? Because the base kinetic energy depends on absolute temperature. So a base thermal energy or the kinetic energy E is equal to 3 by 2 kBE. 3 by 2 kBE. Now we substitute the value of T. 3 by 2 kB. 1.38 into 10 is to minus 23. Temperature is 300 Kelvin. So its answer is 6.21 into 10 is to minus 21 joule. There is a base thermal energy of helium atom at room temperature. Now second, temperature of the surface of the sun. Temperature of the surface of the sun. This temperature is 6000 Kelvin. 6000 Kelvin. Substituted here, therefore E is equal to 3 by 2 kBT. So 3 by 2 kB, 1.38 into 10 is to minus 23 into 6000. So 1.24 into 10 is to minus 19 joule. There is the base thermal energy of the helium nuclei or the atom on the surface of the sun. Here only we have to substitute different value of temperature. And now third is the temperature of 10 million Kelvin. 10 million Kelvin, that means T is equal to 10 into 10 is to 6 Kelvin. That means the 10 is to 7 Kelvin. Therefore, a base thermal energy of helium nuclei or the helium atom is E is equal to 3 by 2 kBT. That means 3 by 2 kB, 1.38, 10 is to minus 23 into 10 is to 7. 10 is to 7. Therefore, simplification is 2.1 into 10 is to minus 16 joule. There is a base thermal energy of helium atom at 10 million Kelvin temperature. Page numerical that may be asked for the objective type question MCQ, because only we have to substitute the value of the temperature. And also we know that the wave translational kinetic energy of molecule is directly proportional to its absolute temperature. Here for different temperature are given. Therefore this wave kinetic energy is also known as the thermal energy. So this way we can calculate the base thermal energy of helium atom at room temperature. Its value is 6.21 into 10 is to minus 21. Room temperature is 300 Kelvin. Temperature of the surface of the sun is 6000 Kelvin. Substituting the value of temperature as 6000, we obtain a base thermal energy of helium atom is 1.24 into 10 is to minus 19 joule. And at temperature of 10 million Kelvin, 10 million, that means the 10 into 10 is to 6 Kelvin, that means the 10 is to 7 Kelvin. So by substituting the value of temperature T is 10:7, we obtain the best thermal energy of helium atom is 2.1 into 10⁻⁻16 joule. Clear? So here the numerical of this chapter are completed.